Okay, I guess we're ready to go. Hi, my name is Ray Wilcock, and I'm pleased that CSPI is hosting this webinar. I want to welcome you all today. I'd like you to please join the discussion. Please ask your questions here as they come up. We have a lot of content, so we're collecting them for the end, but it will probably be most helpful if you ask them as they come up. This webinar will qualify for continuing professional development credit certificates. It basically will qualify in most jurisdictions in Canada and the USA for about 1.5 hour technical. If you would like to have a certificate for this, please email your complete attendance list using your full name, title, your email, and you can email those to me at rjwilcock@cspi.ca, and within a week or so, CSPI will send certificate to all participants. Just a little bit about the Corrugated Steel Pipe Institute. We have over 50 years of education and promotion. We're considered the information resource for water and soil management. Some of the things we do is we develop new standards. We do a lot of technical bulletins, information and resources. We do guidelines, and we have an education outreach program that we offer to all colleges and universities in Canada. Here's a couple of pictures of corrugated steel pipe, a large span corrugated steel plate structure in BC. On behalf of our members, Armtech, Atlantic Industries, Frontier, and ES Hubble, and our associate and affiliate members worldwide, I am pleased to introduce our speaker today. Art Groenveld is a senior engineer with the Ministry of Transportation, Ontario, in the Engineering Standards branch. Art graduated from the University of Guelph in 1984 with a Bachelor's of Science and Water Resources Engineering degree and is registered with Professional Engineers of Ontario. He has worked for over 30 years in the water resources engineering area, and he began his career with the Grand River Conservation Authority. Art is the expert and leader of the MTO Gravity Pipe Design Guidelines. So I'm going to pass everything over to Art, and he will take you on a journey for the next hour or so. Okay? Thank you.
Thanks, Ray. Just like to say thanks for everyone who's online here today to have the time or take the time to join us on this little voyage that I'm going to take you on. What I'm going to be talking about today is really from a whole gravity pipe infrastructure initiatives perspective that we at MTO here in Ontario have been doing and how it fits with our gravity pipe infrastructure. Briefly, what I'll talk about really is our past, the present, and our future status. We'll also talk about the support documents and tools that we've been developing and some of our future activities. The main initiatives that I'm going to be talking about today are those that are applicable to our circular pipe installations, less than 3 meters in diameter or span, and they focus in around the open cut or direct burial installations. In Ontario, when I look at our provincial highway network, we have approximately 16,500 kilometers of provincial highways. Under all those highways, we estimate there are approximately 50,000 culverts, less than 3 meters in diameter or span. Now, this number could be plus or minus 2,000, 3,000, 4,000, whatever the case is, and I'll talk a little bit how we're trying to get that information towards the end of the presentation. The type of shapes that we're dealing with in these smaller culverts are circular, non-circular, box, arch, and they come in the configurations of multiple culverts at crossings or multiple cells at certain crossings as well. On top of that, we have thousands of kilometers of storm sewers along our highways as well. From our perspective, what we saw in the past, and I'm going to be talking from about 2002, we started having some issues with pipes across the province, regardless of material. So for steel pipes, we were seeing corrosion, deflection, buckling, collapse, and similar with the concrete pipe, we did see cracking, the odd spalling issue were happening with them as well, breakage from other pipe products and buckling, as well as some of the work done at the inlets and outlets were not done in context of looking at what the hydrostatic uplift forces were. And so we had some buoyancy issues in uplift. Run through quickly, Barry, a timeline of the past decade, or a little bit more than a decade now, in which we've been working in our gravity pipe area. So in 2002, as I was starting to say, we did have identified a number of problems with certain steel and plastic pipe materials, and at that time, senior management in MTO put down a moratorium on the use of these particular products until we could get more information. Later in 2002, the plastic products were installed or were permitted for installation. In 2003 was the first study that we put forward to start developing our gravity pipe design. In 2005. Our first step of implementation was an interim implementation in 2006, and at that point we started permitting steel pipe use back on our highways. In 2007 we went through the process of implementing the full gravity pipe design guidelines, and along with that, for those involved in the contract preparation area, we also introduced contract specifications. So we had new construction specifications that we introduced, material specifications, as well as we introduced new coding that we could use on our contracts to ensure that the alternative options were available to contractors and easily understood. In addition, in 2008, we developed a series of highway drainage design standards, and this deals with anything from our surface drainage requirements to storm sewers, culverts, and also towards bridges and stormwater management works. In 2009, we went another step farther, and that was we introduced certification requirements on all pipe materials. And that was our first step in that particular venture to ensure that we were going to get quality products. In 2009, we also started looking at, okay, we have installation happening, but how good is the installation? And so we developed installation acceptance standards. We went through a study in 2011 of looking at new information that has come forward and new sciences that have been finished with the gravity pipe design area, and we did the revision work to our gravity pipe design guidelines, and we finished that in 2014. And so we implemented them fully in 2014, along again with some revised contract specifications, material codes, etc. In 2015, we started another study, and this is to deal with gravity pipe trenchless rehabilitation installation study. And this is looking at trenchless installation methods that are in addition to our open cut or direct burial applications that we are currently following. What I will do now over the next hour or so is go through in a little bit more depth and detail on some of these initiatives. When we first started looking into the whole gravity pipe work, from the gravity pipe full infrastructure point of view, we identified that there were certain fundamental, what I call, building blocks. This way we felt that if the right designs could be produced and that we could use specify the right products, have them used properly and installed properly on the construction contracts, and ultimately after everything was said and done, perform the right maintenance on these particular installations, we would have something that was actually fundamentally sound. The word right I have in quotation marks, and that's really because I want to say that it's really based on the science, knowledge, and experience of the day. So as these elements improve over time and new knowledge is gained or new science research has been completed and further experiences that we're gaining, these things can all be changed or revised over time. So if I look at the way we were doing things pre-2007, remembering that in 2007 was the first time we actually implemented our gravity pipe design guidelines, when I looked at the design quality block, there are certain elements that or key ingredients that came forward. Our design service life, our hydraulic analysis work, our joint evaluation on our systems, the estimated material service life, structural analysis, and any unique factors as applicable to a potential site. If you look in the second column here, which says past pre-2007, you can see that there are some blank squares along the way. These are blank because I found that either the work was not being done or the activity was not being done, or if it was done, it was very inconsistent. Some projects or contracts did have it done, others did not. When we did hydraulic analysis work, we would pick one pipe type being smooth or corrugated inner walls, and the hydraulic analysis was done based on that particular pipe. Our designers were not doing any type of structural analysis. That was left to our contractors to finally ultimately decide the strength of the pipe required in order to support the highway infrastructure. Unique factors were hit and miss. Sometimes they were being looked at and other times they were not. Once we moved into our contracts, we found that most contracts were putting forward that contractors would have one pipe material that they were looking at to install, so there were no alternatives being offered. From a certification point of view, the concrete pipe materials were being certified while all the others, if they were certified, was done on a voluntary basis, but it was not a requirement for our contracts. Installation inspections, if they were being done, were visually being done where you kind of hold up your thumb and take a look at the installation, looks good or doesn't look good. And finally, our inspections from a maintenance perspective were really more of a qualitative basis rather than a quantitative basis. And so with that, I'll start off with introducing what we developed in 2008, which is our highway drainage design standards. As you can see on the left-hand side, the bookmarks are available. The SD stands for surface drainage, so these are all our standards that are applicable to surface drainage requirements. So here you see our flow spread requirements, storm sewer system requirements, roadside ditches, gutters, and a number of things involved with our surface drainage. Taking a quick look at SD1, this depicts the design flows for all our surface drainage systems. And so as you can see, based on the functional road classification on the left-hand side of this table, and depends on what kind of road we're looking at, whether it's a freeway, arterial urban setting, collector, local road, depressed road, and our drainage system type we design for minor systems and major systems. In most cases, our minors are 10-year design flows, and our major systems are 100-year design flows, with the exception of depressed roadways, where 25 years are minor flow design. These were put forward as the level of risk that we are willing to take on our structure or our infrastructure in order to maintain continuity of traffic flow and maintain as much as possible a safe environment for our traveling public on our highways. The fundamental use of this particular type of drainage system is really to collect and move water off the surface of the highway and on into receivers. Again, on the left with the design standards, you'll see now that the acronym or the starting designation is WC, which stands for water crossings. A little bit further down, you'll see here SW, which is our stormwater management standards. And finally, there's TW, which is our temporary work standards for activities that are happening on the construction site and how we deal with collection of sediment erosion ponds, etc. So with our WC water crossing standards, we again, looking at our design flows, depending again on the functional road classification, we have spans less than 6 meters and greater than 6 meters. So all our small culverts that we're looking at, for example, will be less than 6, and so our design flows are really the 50, 25, and 10-year. On the far right-hand side of the table here, you can see we have a check flow for scour, and for each type of roadway, it's a percentage of our 100-year flow rates. It also notes here that the fish passage design flow is in another standard, which is WC12. Quickly bringing up WC7, it's our culvert crossings on a water course, and this deals with flood depths at the head upstream face of culverts. And we've expressed it as a ratio of our flood depth to the diameter or rise of the culvert, an HW/D ratio. So again, depending on the functional road classification with the flows, you can see that our HWD ratios for less than 3 meters in span or diameter is the HW/D ratio with D is less than or equal to 1.5. Greater than that, you see the different headwater ratios. That will come into play a little bit later on, and this is really to look after ways that we can look at the pressure flows going through our culvert crossings, and that way we can look at, okay, potential hydrostatic problems with the culvert at the inlet or outlet, as well as looking at what the mitigation or migration of waters outside the pipe walls would be through the embankment rather than going through the pipe itself. So in 2007, as I said, we introduced the MTO gravity pipe design guidelines. It was done in a couple of years of development work in which we researched a lot of the available information, the available practices that were being done by other road jurisdictions, and came back with a complete set of guidelines for designers to follow with all our highway applications. What we do here is that we start off in the context that with our provincial government, the overriding policies that I have to work with really is that there will be a competitive procurement of goods and services for all activities that the Ministry of Transportation does. So with that in mind, we started off with giving, all right, what kind of materials are we willing to accept on our highways? And I'll get into that in a little bit more detail in a moment. But we started off that we wanted to make sure we gave equitable consideration for all pipe materials. Moving forward from that, through the analysis work that would be done by the designer, we then get to a point where the appropriate pipe materials would be specified in a contract, and that way the inappropriate ones or non-suitable ones would not go into those contracts as a choice. And finally, like I said at the beginning, this was to maintain a competitive construction and supply environment for all our contracts. So it's open, all our contracts are open to registered consultants who are with the ministry that can bid on any contract, and it's also open to any pipe supplier of various materials that have been noted as being acceptable or appropriate in our contracts, that they may also provide bids to the contractor to try and supply the contract. This is the gravity pipe design guideline itself, and as you can see on the left-hand side, I've displayed the bookmarks, which are towards the different sections within the document, different listings up at the front, and then there are the various chapters. And we'll go through each of these chapters in a little more detail, as well as there's some appendices at the end with examples. There's different figures that we use throughout the document, different tables, maps, and then a complete listing of the abbreviations that we use throughout the document as well. So it's fairly relatively easy to use and straightforward in the approach that we've taken. Highlighting the design process in itself, it goes through basically 8 steps. The first one is really trying to set up, okay, what's really needed or required at a project. And from here, the designers will actually start looking at various elements of the project to try and set, for example, the DSL, which is our design service life, and other criteria. Pipe size and type availability. Well, this part really reflects commercially what's available for our choice to address the hydraulic conveyance requirements at any given site on our highways. Each of the pipe materials have various types of joints that are available, and depending on the ground condition, groundwater conditions, etc., some choices need to be made here. As I said earlier, one of the steps from a durability side on material was one that was very inconsistently or not applied at all in the early stages of design, and we now require every designer to go through that process to ensure that the material has been fully assessed as far as its ability to potentially give us what we're looking for in the design service life. Once we have all the different pipes set up or selected at this point based on the initial hydraulic assessment as well as the durability assessments, we now run into the context that there are certain variations in pipe sizing that comes into play, and so we need to ensure designers also do final hydraulic analysis to ensure that the pipe culvert or the storm sewer delivers on the flow regime or the flow variances that we're going to be looking at. Once that's all said and done, we're also moving forward that the pipe in itself in the installation side must also support the highway, support the loadings from the highway, be it static loading and dynamic loading. So again, the designers are required to do this full assessment now. Life cycle cost analysis, we've introduced that one so that you can do solution cost comparisons. And finally, writing a document like this, it's very hard to try and envision every type of situation that we're going to run into. And so that designers in the end will also have to take a look at, okay, do we have anything unique or very special to a particular site that needs specific addressment that the gravity pipe design guidelines process did not do in itself. So highlighting that, just the process. There's also this flow chart in the gravity pipe design guidelines, which again takes one step further to define or give a little bit better indication on what's required at each step of the way. So as you follow through, there are decision points that, is this pipe suitable or not suitable? If it's not, we're not going to consider that particular product any further, and we keep moving forward with those that are actually suitable. So given that there are a number of different pipe materials available for consideration at the beginning of the process, it's an elimination decision process along the way from that point on. If the pipe material can deliver, it continues through the process. If the pipe material cannot deliver to a certain element, then it's eliminated from further consideration. So by the end of the process, we have a complete list of all those products that are acceptable for the installation at any given site on a highway contract. Going a little further now into our step one, if we look at it, the designers start off and they're going to have some sort of a functional highway configuration, and that may be 2 lanes versus 4 lanes versus 4 lanes with a median turn lane, a divided highway cross section with a median barrier, or it could be divided by a median ditch, the urban cross section versus rural cross section. They take all these things into account to start determining whether or not it's going to be serviced with storm sewers or drainage ditches and culverts or bridges and so on. We have in place, again, from a ministry's policy perspective, what we call Directive B14, and it's our drainage management policy document, and it outlines our requirements under statutory and common law. And so as our designers are putting the system together, they're following along with the direction from this directive to ensure that we do not compromise or cause undue hardship on other landowners upstream and downstream. We already talked a little bit about our highway drainage design standards, which gives us the design criteria for all our storm or sewers, or culverts, bridges, etc. Design service life. Functionally, we're looking at it that we have a 75, 50, or 25 years in place, and it really comes back to the designers again to start looking at some of the context around that as to which design service life is what we're trying to aim for. Fish passage habitat needs possibly come into play here, so we may have to look at low flow channel construction in a culvert. We may have to look at providing baffles in order to ensure that fish can migrate through the culvert upstream. We also have other engineering disciplines that are a part and parcel of the highway contract. So there's foundations engineering, geometrics, electrical, traffic, and they all have needs as well on that particular highway. And the drainage engineer will try and make sure that whatever he is designing complements any of the other discipline requirements. Finally, one other element that I wanted to bring forward during this talk is that we also want the designers to start looking at, okay, what's happening with this highway in the future? Like, is this a fix for today so that we can get down to the major contract that will be happening 25 years from now or 10 years from now? And so they may take a little bit of that into context of deciding what kind of a design service life they may apply to this particular project or site. With the design service life, when we looked at the highway functional classification, we have what we call our 400 series highways, which are major freeways throughout the province. Our secondary level, which are the more rural type, although they can be up to 4 lanes in size, and they can have rural cross sections as well as urban cross sections. And there's also the local roads that we also look after in certain parts, especially in northern Ontario. So we have 75 years for those 400 series highways, 50 years for the secondary level highways, and 25 years for the locals. Again, depending on the point of application, ramps on the 400 series highways may be deemed to be requirement of 50 years because they're easier to access, cause less traffic disruption. So there may be some decision on the design team of varying the design service life requirements throughout the project. First step in the process of the pipe materials is that there is what pipes are going to be considered. And so what we've done is looked at it from the different material side, and you can see here on the material column, we're looking at concrete material, steel, high-density polyethylene, polyvinyl chloride, polypropylene, and aluminum alloys. These are the materials that, given the industry standards, which is in the second column, are all applicable to either culvert or to storm sewer applications under highway conditions or other local conditions, our interest mainly being the highways. Within each one of those particular standards, industry standards, are specified these other parameters with each pipe material of size, type, and class. Size is relatively self-explanatory. Type, we're really looking at two types of pipe materials. It's either a corrugated inner wall or it's a smooth inner wall. And from there, the class is really the material specifications. So you can start seeing that, okay, we have reinforced concrete, non-reinforced concrete. We have different wall thicknesses. With the steel, we have wall thicknesses as well, and we have protective coatings of galvanized, aluminized, or polymer coated or laminated. With the plastic pipes, we're moving more into a stiffness or ring stiffness constant or dimension ratios. And again, with the aluminum alloy product at the bottom of the table, we're looking at different wall thicknesses available. These are all commercially available products, and so within the gravity pipe design guidelines, we've actually managed to capture all these commercially available sizes. They're available in Appendix C, and here you can see the different types of tables that are associated with each of the pipe materials. Each one of the tables lists the diameters involved, the corrugation depths in the case of steel. We also have the inside diameters, the type of joints that are available, Manning's roughness coefficients that are available, outside diameters so that we can take into account the wall thicknesses. So a lot of information is available, and so for the first step in the design process really is looking at, initially hydraulics are telling you you need something like 1,000 millimeter pipe size. What's available in that 1,000 millimeter category? As well as that, we also ask designers to start looking at the size tolerances. So the tolerances is how much bigger can that pipe be and still deliver to the hydraulic regime requirements of the location. In some cases, it may be able to be increased by 200 millimeters in size. In other cases, it may not be. So designers are able to not only look at what's the minimum size available, but the opportunity to look at any larger sizes that are appropriate for that. Part of that is that we have it all defined in a category basis. So if I say the 1,000 millimeter pipe culvert category, we're looking at all pipes that are 1,000 millimeters up to 1,099 millimeters in diameter. If you start looking in a little depth and detail into these particular tables, you'll notice that there's some at 1,000, there's some at 1050, there may be 1080s, 1070s. So there's a variety of sizes available in our 1,000 millimeter category. We've done this in order to be inclusive of all sizes available. So as I said already, the initial hydraulics then is really looking at the size and tolerance. The different materials, you can see that we're looking at smooth or corrugated. And so you can see that steel has both smooth and corrugated available, while the rest are all smooth with the exception of aluminum alloy, and that's a corrugated product. Based on slope and length, we're now able to start zeroing in on the size requirements of the pipes, materials that we accept and are available for use on contracts. Joints was the next step of our evaluation process, and based on different site conditions, you make a selection as to the type of joint that's needed. We also went through the types of joints available from every pipe product and have been able to come out in the context of 3 different types of joints: soil tight, silt or fines tight, and leak tight. The suitability of each of these different types of joints really comes about in the site conditions that are encountered or the type of fill material that may be used. So that soil tight pretty much is used in areas where your fill material is coarse with a small percentage of fines, and exfiltration or infiltration of water is not an issue. Again, where it's not an issue but you have a high percentage of fines, you can move it over to a silt fines tight, and finally if the infiltration of materials or waters is an issue, you move to leak tight. What we have in our process is setting it up saying that, okay, if a soil type has been specified on a contract, that's not to say that if the contractor wants to put a pipe in with silt fines tight joints or leak tight joints, that's also acceptable unless it's been specifically stated by the designer that it's not. And we'll talk a little more about that. Within the gravity pipe design guidelines, we again have tables that are available so that you can look at the different pipe materials, the different type of joints that are available, and what they're actually classified with as being soil tight, silt tight, or leak tight. Keeping in mind why the joints are there, really it's to connect the entire system, and it's going to go through some different stresses and strains as well. And so really you're looking at joints that are going to provide either some resistance to something, or it's going to allow accommodation of something else. So we want to keep the pipe sections together so the joints should be able to hold every section in place. We also wanted to make sure that it's held in place so that we can maintain the hydraulic continuity throughout the system. If we start having offsets, then the flow regime changes, and that could have implications at the outlets. We also want to be able to accommodate any lateral or longitudinal movement so we can prevent certain structural problems. Sometimes if we're too rigid, we may be causing further problems. If we're too slack or too flexible, we may have aggravated problems as well. So the designers, again, need to be looking at that. Finally, with the resistance or accommodation, you start looking at, well, if we put a storm sewer system in where the groundwater may be slightly high, we don't want to have it functioning as a tile drain and start dropping the groundwater table in an area. It would have certain environmental implications. If we're within water source control zones, now again, it's sourcing water for private well applications. We want to make sure that the waters in our area do not contaminate those sources. With water flow levels at the headwaters of our culverts, here's where we bring in the headwater to diameter ratios. And what we're looking at is that between 1 and 1.5 for our design storm event, and that was either the 10-year for our surface drainage, or it could be 25 or 50-year for our culvert applications. Then we're looking at that a silt tight is okay, or we recommend that it should be okay. And again, silt tight or leak tight could also be used. From a major storm, which is the 100-year, or it could be our regulatory storm, we're looking at if it's greater than 1.5, then a leak tight joint is recommended. This is dealing with actually the headwater pressures that will be forced on the culvert crossing. Again, where environmental sensitive areas are encountered, leak tight joints may be required in order to ensure that we don't impact adversely the environmental area and its function. Having gone through the process now, we have pipes that are of adequate size to deal with the hydraulics or the hydraulic conveyance requirements. We've also looked at the various type of joints that we need to have at the site and have picked pipes now that are able to deliver to those requirements. So the next step of the process is looking at these particular materials and looking at the effects that are going to happen on them as far as what durability is. In other words, we're trying now to estimate how long the material will last from an estimated material service life perspective, and whether or not that will exceed the design service life set up for each of the different site locations on a highway contract. Various factors affecting it in the corrosion could be the water chemistries or soil chemistries or other agents, solvents. Mechanically, there's abrasion factors, humidity and temperature potential, and the material composition to some extent as well. This is all discussed in Chapter 7 of our guidelines. Throughout Chapter 7, with the different materials, as you can see listed on the left column, our estimated material service life is either calculated or it has been assigned based on information that we were able to gather. We provide guidance throughout the document either through narratives, charts, equations, graphs, etc. Here's a table of in our Appendix C for concrete. But depending on the pipe slope, depending on the diameter, you can see on the far three columns of the table what's the minimum pH needed to attain those EMSLs. So if you've taken the water chemistry measurements and your pH levels are greater than those indicated in these particular columns, based on the slope of pipe that you've installed, you have your concrete pipe able to have EMSLs greater than the design service life. The final line is in cases where the pipe is going to be installed at a slope greater than 10%. A more detailed analysis is really required in order to ensure that the pipe material will actually give us the durability requirement. This is the table for aluminum alloy, and we have estimated corrosion rates based on the pH or the resistivities. So you can see on the left we have the pH ranges over in this area here, as well as the estimated corrosion rates per year. And on the right-hand side of this table, right-hand half of the table, it's resistivity based, again with the estimated corrosion rates. So given your pH and the resistivity, the greater of the two corrosion rates would be used then to be applied to your material thickness to determine, is this particular thickness good enough to make it to the design service life or better, or do you have to get thicker pipe material walls in place in order to deal with that? From steel pipe perspective, 2014, again knowing the pH and the resistivity, if at any time your point of intersection is above and to the right of these different lines, you have a pipe product then suitable or has the potential of meeting your EMS or DSL requirements. The black is the polymer laminated product, the green is the aluminized, and the orangey colored ones are the various thicknesses of galvanized product. So again, if you're in the 4.5 pH and 2000 resistivity, you're in this particular area here, and your polymer laminated product is suitable. The other products would not be suitable. So again, up to this point, we were able to carry all the different pipe materials with their various coatings and thicknesses forward. Now, through durability, we're starting to zero those down to the types of materials required in order to deliver to the potential of the DSL requirement. The plastic products like HDPE, polyvinyl chloride, or polypropylene products, more or less based on the materials themselves, on the ability to meet 75 years, given the science behind the composition of these different materials. We were able to come to the point of recognizing that these all had the good potential of making 75 years. These have been assigned 75 years and thereby are suitable for pretty much every application on our highways from a durability perspective. Also within the document, we do provide the ability to use equations to calculate what the estimated material service life is. Again, for concrete, we have 4 different models. There's the ODOT model, which is widely recognized and accepted throughout the industry and the road jurisdictions. There's also the Hadripiano model, HERD model, and then there's a Florida model. These are all discussed in more detail in the guidelines in Chapter 7. What I'd like to bring out here is a little bit of additional information that was brought forward in the context of soils and rainfall. It helps you do a little bit of correlation between what you're seeing from sampled pH and resistivity or hardness or any other environmental parameters, and correlating that back to some of the historical performance of a pipe that may have been in that location. This particular slide is sort of the acidic levels of rainfall across Ontario. So you can see in the blue area, we're in a 4.4 or less with pH from the rainfall. The red is 4.4 to 4.6, and then in the purple area, it's 4.6 to 4.8. This gives us an indication of the type of rainfall or the water that's being dropped on the ground in these particular areas of the province. When we start looking at the various colorations of the soils across the province over in the map on the left-hand side of the screen, over on the right hand we have the legend there which shows the various colors and the ability of those soils to do any moderation to the rainfall. When you look at the brown areas, we're seeing that if you're looking at a 4.4 to 4.6 pH level, the soils in the brown areas really don't impact a lot on those particular levels of pH in the extent of more neutralization. So you're not going to see a lot of neutralization happening on that, and you're going to be dealing with very aggressive pH levels on your materials. The green areas have a bit higher neutralization or moderation effect on rainfall, and so are a little bit more open to other types of materials being able to be used in these locations. So now that we've actually gone through the process and we now have suitably sized pipe based on our initial hydraulic analysis, we have the joints, we also have the durability factors played out as far as materials now go. We've been able to reach certain specifications so that wall thickness of certain may not be suitable. These were eliminated along the way. So again, we've been eliminating non-suitable pipes all through this process. When we reach the final hydraulic analysis aspects, because as I mentioned before, there is a range of sizes available if you pick the 1,000 millimeter category once again, there are various sizes available, and do they all act the same way on the hydraulics? For a culvert, we may actually have to look at low flows for fish passage requirements, moderate flows from erosion perspective downstream. We have our design flows, as we noted from our design standards, could be anywhere from 25, 50, 100 year, 10 year for storm sewers, or 25 year for depressed roadways. Major flows that we have to look at are the 100-year or potentially our regulatory storm levels. And we also have check flows for scour analysis, and that would be done at our culverts. So all this is the type of final hydraulic analysis that we're looking at the designers to do prior to moving on into the structural assessment component of the process. This map shows the regulatory storms in Ontario. Zone 1 is really Hurricane Hazel based. This was the storm that happened back in 1954 and flooded a lot of the Toronto area, and this has been deemed by the Ministry of Natural Resources as the regulatory storm for all development in Zone 1. Zone 3 is our Northern Ontario levels, and that is based on a Timmins storm that happened back in 1972, I believe. And that again was one of these two storms were the most intense that we had experienced in Ontario in these locations. Over in Zone 2, this is really the area where the 100-year storm levels are applied as being the regulatory, because the influence of Timmins and Hazel did not extend to those areas. So for all our designs where they have to do any regulatory analysis work, these are the regulatory storms that they would actually input into the hydraulic analysis component to look at overtopping relief flow aspects on highway crossings at bridges or culverts. Moving forward into the structural component, one of the things that we found when we were looking at these contract specifications really came about that they were specifying rigid pipe and flexible pipe. And rigid pipe in the context of designers was any pipe that had a smooth interior inner wall. Flexible pipe was anything that had a corrugated inner wall. Well, in the context of the materials themselves, rigid pipe is anything that cannot deflect more than 2% without cracking, versus flexible pipe that can deflect more than 2% and with no cracking as well, but it actually will be able to deflect more than the 2% level. So really when you look at a rigid pipe, it's the concrete material versus the flexible pipe, which is our steel and plastic products. In the context of the installation, you can see that with rigid pipe we're looking at 3 distinct layers when the contractors would be performing their backfilling operations of bedding, cover, and backfill, versus flexible pipe installations, which really have only 2 layers, the embedment layer and the backfill layer. Our designers at the time were never specifying exactly what type of materials are needed for the bedding or cover or embedment or backfill. This was all left up to contractor choice based on some level of input from the foundations area. And a lot of times what we were seeing is that the bedding is not appropriate or the cover was not appropriate, and thereby we were having some insulation issues and the culverts were not operating to our expectations. So we moved this forward into the design area to make sure that our designers are actually looking at this and making some design decisions based on the requirements of the site. different ways, or the different aspects of the structural loading conditions. There's a minimum level of fill that usually is associated with the installation, and there's also a maximum level of fill that's associated. And with each one of these, they're putting a static load on the pipe infrastructure, as well as they have the dynamic loading coming from traffic. The installation component also can be either in a trench situation, which is shown in A, or you can have a embankment situation over in B and C, depending on the level that the pipes are being installed at. You can have either positive projecting or zero projecting. We've gone a few steps farther over time and have started looking at the way the distribution of the loads are going across the pipes, and what we're really looking at is that with any structure or infrastructure location, if we can see, okay, what's the lowest level of fill that's going to be at the site, or what's the highest level of fill that's going to be at the site, we can then come out and take a level of analysis on that, determine do we have enough fill to support not damaging the pipe, and do we have too much fill that the pipe cannot support and we need something different in order to support that. So again, with this information, the designers can now take it one step farther, and we have what we call these height of fill tables. This is one for the corrugated polyethylene pipe, HDPE product. And you notice that we have the different diameters, the trench widths that are associated with the installation, as well as the pipe stiffness factors. So at 320 kPa, it would support up to 9 meters of fill based on the analysis work done in this particular table, which is outlined in the notes below. This one here is for the polypropylene product, and it's been done under granular A conditions or granular B, which is a type 1 or 2 composition. Again, different diameters that are available of the commercially available product and the different heights that are available to be supported. And so again, knowing what's the minimum, what's the maximum, the designers can make their choices now to say, does this pipe meet the structural requirements at a location? Again, this is the closed profile polyethylene pipe, different RSC values of 160 or 250, and this particular one, it shows a little bit more with the variations in sizes. As I said, if you looked at the 1,000 millimeter category, which is shown here, it would be 1020 and 1070. Our hydraulic analysis would determine the differences between those two sizes and whether or not both are acceptable. You have the minimum heights of fill and maximum heights of fill that are available or appropriate for this particular product. And if your structural site actually meets those requirements, these pipes would then move forward to the next step. This is the concrete pipe. It's a reinforced one in embankment installation condition. Again, you have your three different sizes, the bedding class that's being put in place or in the design process for the installation, and the different D loads of the pipe, 50D, 65D, 100D, and 140D. So again, depending on the height of fill available, the designers would then be able to go through and make a choice of what's the loading or the D load factor that needs to be applied to this particular location. So having gone through now and finally come down to a point where we now have all our suitable pipe materials that are able to satisfy the hydraulic criteria, the durability criteria, joint criteria, and the loading criteria, we can now look whether or not a life cycle cost analysis is needed. What we found in our analysis of that, really it more came down to what's the cost of one-time pipe installations as compared to what we call pipe replacement rehabilitation strategies. So with a one-time pipe installation, we're looking at all the suitable materials as they have come forward as having a estimated material service life greater than or equal to the design service life, versus the pipe replacement / rehabilitation strategies are those where select materials probably have EMSLs less than DSL. So we could look at potentially putting in pipes for 25-year service life into a 75-year design service life situation. This would require 2 replacements of that. We can cost out that to see whether or not it's more advantageous to go that way versus the one-time installation. The other one may be that we could put in a pipe product that allows for us to insert a liner in future. So we have opportunities to look at different ways of dealing with that particular site in the future. This way, we're trying and get our designers to look more proactively into the future to see if we do this, what will happen when we get to year 75 years down the road. So we start making some earlier decisions in that we can then start looking at larger pipes potentially. We can look at setting up the construction or the installation of the product in a manner that we can, say, employ another type of technology to put a new pipe in place. So up to now, what I've pointed out or put out on the table so far is that what the gravity pipe does is that it gives you, or gives our designers, a systematic design process. It was one that they can follow and highlight the different steps or the different tasks needed to along the way to ensure that they come out with suitable products at the end. These standards that we've put forward and the criteria put forward ensures that we try and look at all the risk associated with it to the fullest extent possible that's available to us today. What I will say also is that this only provides you with the designers with the minimum material specifications for each acceptable pipe type and or product and material. So what we're really looking at is that this process was focused at trying to get designs that are reasonable and cost appropriate to the best extent possible. What it does not do is actually be able to address the certain unique site or project situations that are encountered. We cannot address everything, and we have to leave some of it up to the design team to make some decisions on. The system anchoring requirements really is dependent on slope steepness. We started seeing that pipes on 20% slopes really require a little bit of support anchoring in order to ensure that they remain in place over time and also to maintain connection stability. In some of the problems that we did see on some of our sites was that there is the piping phenomena happening around the outside of the culverts or the pipes. And what we're now asking the designers to also make sure they look into is there a need to prevent water migration around the pipe, and that would be in the terms of clay seals, anti-seep collars, cut-off walls, and buoyancy factors, head walls maybe, or wing walls in order to keep the pipes down in place and not subject to the hydrostatic uplift forces. In certain cases, changes may be required that would entail getting ministry approval, maybe some would not. How we've been dealing with the requirements as far as the head office type of approvals, in a lot of cases there's unique situations that are encountered right on the site. This might be in terms of fish passage that you need to put in baffles, and the baffles are a type that are being put forward that are conducive to being put in one or two pipe materials, but not in the other two that made it through the process. Design team at this point can also eliminate the other two that are not suitable based on what they have requirement. Might be that we have endangered species or species at risk. It might be a human passage requirement. So if a pipe material can't deliver to a certain element that they've encountered on a site, these pipe products are eliminated by the design team. Other cases we find that as the design team puts a highway concept plan together or a detailed design plan together, we may end up seeing that they have multiple options of what they can do at a certain location. The region will, based on costs or availability of getting the work done or availability of expertise in the area, may decide to go with one option over another option. And if an option tends to be material specific as far as pipe is concerned, the design team can make the decision to eliminate those pipe materials not suitable to that particular option. Might be that we're doing a highway transfer to a municipality. Thereby, we usually bring the highway up to municipal standards prior to handing over the highway to the municipality. We would work with their criteria, and the design team would make choices based on those requirements. It may be a regulatory agency requirement that causes us to go a certain direction as well. At some point, though, we find that, okay, we may end up in a situation where the design team really feels that the minimum as put forward by the gravity pipe design process is not enough, and they really feel that something more should be done. They can actually do a justification report and submit that to head office for approval. The reason for doing it in this manner is that we are also at this point then collecting the reasons or the requirements as put forward by these different requests, so that in the future we're going to be able to take these and incorporate them into the design guidelines at some point, that we don't have to keep on doing this particular approval process. So currently right now, if we're looking at, say, a highway situation where the design team really is looking at this as saying, okay, the minimum, because of the complexity of the site, may not be the best here. And really what we might want to look at is one specific material to give us the better possibility of meeting our 75-year design service life requirement. Maybe looking at the recommendation was the second level of specifications from the pipe product. However, there are two higher ones available. Maybe we should go to the higher one right away and be more positive about reaching our design service life. Decision might also be made here to try and install larger pipes to service it for the time being, so that at 75 years in the future we can insert a liner perhaps into this particular location to provide the functional hydraulic requirements at that time. Or it may be construction of a pipe envelope around the pipe installation that would allow a pipe ramming operation to be done in future, or a tunneling operation. So there are different ways that we're having our design team start looking at where we are going from today into the future. So with this, what we end up with at the end of the design process is a what I call an equitable alternative pipe materials list. These are all the pipe materials that you're seeing that have come out through the hydraulic analysis work, the durability analysis work, the structural analysis work, as well as considerations of unique conditions that are then going to be moving, or should be moving forward into the contract for the contractor to put in place. This is the way that we actually put pipe material alternatives into our contracts. And so the contractor now has choice of installing any one of these different type of materials that are listed. With this particular one, we're seeing that we have 22 acceptable products that would go forward into our contracts. How do we get them into our contracts? And now we're moving to the next block, which is our pipe contracts block. In the MTO contracts, what we use are what we call pipe quantity sheets. So there's one for pipe culverts. I'll just move to a little bit larger size to help anyone see it a little bit better. But on here, we have all our details for the contractor to know about in order to install the pipes in the different locations. So you'd have your culvert numbers, locations, where it's located on a highway, any details as far as the SKU number, depth to pipe, the type of bedding, cover, backfill, joints, treatment, upstream and downstream invert elevations. The actual pipe tender items we would actually locate up in these squares on the upper right-hand side of the quantity sheet. On the lower left-hand portion of our quantity sheets, you see these legends. This is the information that's put forward for contractors to know exactly what is being specified in the contract. We have one here, as I said, for culverts. We also have one for sewers. So again, it's all been put together in trying to, or put forward the actual details that the contractor needs to know in order to install the pipe locations. Blowing up the code a little bit more, you can see that we have material code on the upper left-hand side with different digits. I'll talk a little more about those in a moment. In the center portion of the screen here, you see there's pipe type again, S for smooth, C for corrugated. The joints, soil type, silt fines type, leak type, type of end finishes, frost treatment or paved inverts or fish baffles. All this information is put forward to the contractor, as well as the fill materials, the different designations for the different types of fill materials that we have. And it's also sort of in a hierarchical process as well for most cases, that if G were put forward as a granular requirement for the bedding, then the contractor has choice of using either granular A or granular B type 1, 2, or 3. And you can see the other designations of B and A start restricting it a little bit more to the contractor. these are these little squares that I was pointing out earlier on our contract quantity sheets where our pipe tender items are put in, and you can see that the tender items are composed of either 3 lines or 2 lines. The first line is our category item. As I said, in this case it's a 900 millimeter pipe culvert, and it includes all pipes that are sized from 900 up to 999. The second line here is the 900 plus 75S, and 6 more numbers, and I'll talk about those in a moment. But looking at these first 900 plus 75S, we're now saying only smooth pipes 900 up to 975 can be used. So this plus 75 is the tolerance range that the design team determined through hydraulic analysis. They also did the analysis in both a smooth and corrugated situation and deemed that the 1,000 plus 50 corrugated products were acceptable at this site as well. So you're looking now at 1,000 millimeters up to 1,050 millimeters in diameter products. Just highlight here that we were able to use the same type of designations with the non-circular pipes, and they're not actually addressed 100% in these gravity pipe design guidelines, but the material aspects are much the same, and we have applied them there. The pipe material code, which is these last 6 digits, as you can see, each digit, it's not a number, each digit represents a material. So the first digit represents concrete and ranges anywhere from 1 to 5. The digits in themselves denote the different D loads for the product. So 1 is 50D, 65, and so on up to 140. The second digit represents the polyvinyl chloride polypropylene products. 1 is the PVC and 2 is polypropylene. The third is HDPE, two levels, open profile HDPE products or closed profile products. And the fourth, fifth, and sixth digits represent the steels. The fourth is for galvanized. The fifth is for aluminized or aluminum alloy products, and the sixth is for the polymer coated or laminated steel products. The different pipe wall thicknesses are denoted by the different numbers that would be located in that 6-digit location, or fourth or fifth. So if I look now at the code on this particular one I'm using as an example, we have a 22321, the first digit. The first number is a 2, which denotes 65D, and it could be 100 or 140D, depending on what a contractor may have available from previous jobs. So the second digit, again, is a 2. Polypropylene is the 2. PVC is 1. PVC would not be permitted in this contract. The third HDPE value is 2. You see it that it's a closed profile pipe only that would be allowed in this particular location. Again, the fourth, fifth, and sixth are again 3, 2, 1, and going back, if you look at 3s would be the 2.8 because we're talking about the smooth pipe at this stage. The 2 is a 2 millimeter thick, the 1 is a 1 millimeter thick, and it's polymer based on the location, which is the 6th digit. The second line of code for corrugated pipes denote the material values. Currently, to my knowledge anyways, or to the knowledge we have at this point in time with our design guidelines, there are no corrugated products available from concrete, HDP, PVC, or polypropylene, so we only have the steel products to consider for corrugated, and again the coding put forward there. So if now again bringing back the pipe culverts quantity sheets, we can see now that there's a lot of information that goes into these particular documents. So with the depth to pipe, the contractor is able to estimate the type of quantities he's going to need for the granular fills or native fills, the type of joints, the treatments required. As I said, they're all identified in the legend. It has now the inverts to work with, determining the slope, the various pipe tender items, the different lengths. Down at the bottom you can see that these 3 columns are kind of pulled together, which are all the same category, but material specifications are slightly different. So this is what we call a composite tender item. The suitability of this particular way of putting it into contracts is that everyone, contractor and pipe suppliers, can now look at these different codes and know exactly what products can be supplied and installed on a contract. In 2009, we moved forward with another step in the gravity pipe infrastructure initiatives, and that was certifying or requiring certification requirements on all pipe materials. Prior to 2009, the only product that we had that required certification for installation on our ministry contracts was the concrete pipe material. So in 2008, we worked with the different industries to determine how certification could work with each of the different types of materials. And we started off that, okay, Standards Council of Canada accredited certification bodies. With that, we found that there are 4 main bodies in Ontario that we can work with as far as certification of pipe materials, which is CSA International, NSF International, Canadian Welding Bureau, and Intertech. With CSA, they actually do certification of the HDPE, PVC, steel, and aluminum alloy products. NSF does HDPE. Canadian Welding Bureau does the steel products. Intertech does the HDPE, PVC, and polypropylene products. So really it's more up to each now pipe industry plant to ensure that they've received inspection by an accredited certification agency and that they've granted them the license to put or to distribute certified pipe products. With the concrete industry, it's already in certification process, and this was done as a group with the Municipal Engineers Association of Ontario, MTO, and the every concrete plant has to go through that to receive certification. We have our contract specifications, and there's construction specifications, and there's also material specifications. Pulling this one up from the polyethylene product, this gives you sort of the table of contents, all the material aspects that are discussed within this specification, as well as on the right-hand side here, you can see the different logos from the certification agencies. These logos are what the contract administrators on our contracts look for. The pipes coming into the construction site must have these logos on them, and these logos must be in the frequency as determined by the industry standard specification requirements. So the intervals on a pipe as far as markings go must be done in accordance with that particular standard. So if you start looking at the pipes that we'll be seeing out on the field, you can see that the different pipe materials have different certification logos placed on them, and this is what our contract administrators will be looking for. No logos, the pipes will be rejected. As I mentioned in the opening remarks, we also identified that we had some installation problems, that certain times we were looking for different types of installation methods that were being used that should have been used that didn't seem to be used, and we were seeing failures on our pipe installations because of that. We brought into play in 2009 what we call our installation acceptance standards. We have 4 levels. One is acceptable, and we do no price adjustment. We have a range of what we deemed as threshold, where according to the industry standards of application, the installation should have been done or could be done up to this level. However, the contractor didn't follow the specification appropriately and constructed outside the level that could have been done. Not really worthwhile ripping it out, and so what we do is impose a weighted price adjustment of 85 cents on the dollar. From a repair perspective, again, damage to the pipe and the contractor has had to repair it and is not taking it out, and we're imposing a 75 cents on the dollar price adjustment. Main reason for both those is that we did not contract with the contractor to put in pipe installations that were substandard. Slightly substandard we'll live with, but we're not paying a full dollar for the work being done. So this is really looking more at quality of workmanship as done by the contractor. For a reject, the pipe has to be replaced at the contractor's expense. We do a re-inspection of that particular pipe location, and depending on if it falls into threshold or repair elements, it would be subject to price adjustments, as I talked about at the upper part of the slide. This is in our construction specification standard for culvert installations. In the specifications, we have a table of pipe condition codes, the different types of codes. The letters denote something, so the context of what you're seeing on the left-hand side here would be FS, which is a spiral fracture on a concrete pipe product. H is a hole in the pipe. D is for deflection or deformation, depending on the way of the getting the deformation levels. If the pipes are too big for equipment, it's done by visual tech. We have some standards in place for those. We also have the equipment side and the pipe size. If it's less than 750 millimeters in diameter, there is a threshold range. Greater than 750 millimeters in diameter, there is a again, the threshold range and the reject range. But the reject range stops at 7.5% because the larger the pipes are, the easier it is for them to install. What I will point out here also on our construction specification is you'll notice that it says OPSS.prov. This is an Ontario Provincial Standard Specification, provincial. So this is the designation that this is used by the Ministry of Transportation only. Another counterpart to this one would be OPSS.MUNI, MUNI, and that would be used by municipalities. We have some variations in the way we do things as far as culvert installation work goes, namely the inspection side. Thereby we have two different types of standards for this. The pipe condition codes that I've talked about come from the Manual of Sewer Condition Classification, and this is the documentation that's used by NASCO inspectors. These NASCO inspectors are certified, and they're the only ones that are accepted as far as being able to inspect pipe installations and assess them. Our inspections are done on a statistical basis. When we go on to a contract, excuse me, depending on the amount of pipe culverts or the amount of sewer item lengths, if we have to do, if the inspection work is required, 25% of the culverts are inspected, as well as 25% of each sewer item length. There are triggers in place, and the one that I will put forward is that if more than 10% of the pipes inspected are threshold as far as the status goes, we will initiate additional inspections of 25% more of the pipe product. If these triggers are initiated once again after the additional inspections have been completed, we will then actually go in and inspect the remaining installations. Once the additional inspections start kicking into play, these are all at the contractor's expense. So typically what you might see on something of an inspection would be a CCTV camera inspection, which is the inspection video on the upper right. And on the left you'll see a laser profiler inspection. And down on the graphical component of it, you'll see the deflections as measured by the laser profile as it went through this length of pipe. What you'll see here is that we have an acceptable rating of 5% or less on this particular pipe product. Threshold rating is at the 7.5% or less but greater than 5, and then our reject rating is greater than 7.5%. The blue line indicates the level of deflection on this particular pipe product, and this would be one that would receive the reject status after inspection, and the contractor would be required to replace this one at his expense. And finally, having all this installed, we're into operations, and we had a look at our maintenance practices. If anyone remembers back to the initial slide where we had qualitative maintenance inspections being done, we introduced new inspection protocols and requirements in 2010. And it's broken down into the elements that surround the culvert, so your water course, embankment, pavement, inlet area, outlet area, and then the culvert itself based on material shape and joints. The surrounding elements are 0 to 2s, and the culvert themselves are 0 to 4. The 0 to 2s relatively easy to fix, some new fill material on the embankment to take out some of the eroded or fix up an erosion area. The culvert in itself is not affected. Once we start getting to the culvert being affected, usually tends to be 2+. All this then is transcribed or transformed into what we call a culvert maintenance index. It ranges from 0 to 100%, and it's a quantitative basis. It gives us more of a proactive versus reactive approach. So based on the culvert maintenance index, which is in your column on the far right-hand side, you can start seeing what's the course of action as denoted towards each of these culvert maintenance indices. Inspection schedules, new installations, there's routine inspections that's done by our maintenance staff, but there's also a detailed inspection, and in this case, for new installation, would have to happen every 10 years if it's more than an 85% CMI. Starts going to every 5 years once it drops below 85, but more than 75. And as we progressively get down and down as far as the CMI is concerned, more and immediate action is required to be done by the contractor, maintenance contracting staff. So kind of summing up what we've been doing up to this sort of point in time with our gravity pipe practices, as I said, when the pre-2007 column, we had a lot of blank spots where it was not done, or if it was done, it was a very inconsistent application of what was required. Moving to where we are today, we now have that we have our DSL set for a project based on highway class or other future contract ideas or anything like that that come into play as determined by the design team. From a hydraulic analysis perspective, we now require both smooth and corrugated pipes to be analyzed, joints based on site needs so that we can make sure that we get the appropriate type of pipe joint into the site location. We now have a estimated material service life analysis requirement to identify what are the suitable materials that can go into a contract. There's structural analysis. That's now done by our design team, and so that we have the suitable materials once again put forward. Unique factors have to be assessed by the design team and any changes made appropriately. With the contracts themselves, once we move into the specifications, all suitable materials are now specified in the contract rather than just one pipe material. At times, depending on the situation, you may see only one pipe material specified, but for the most part, we want to make sure that the design team has looked at all the different materials and deemed their suitability based on the design process. Certified products, every pipe material that's going to be installed on the ministry contract has to be certified instead of just the one in the past. Our post-installation inspections, we now have acceptance standards in place, so all contracts do require some inspection work. We'll have to pass on the acceptance standards or price adjustments may be imposed. And finally, from our maintenance inspections perspective, we're at a quantitative state and that we have a CMI to work with, and we now have a little bit better direction as to what kind of action is needed. For the future, when I start looking at post-2014, which we're kind of in already, things will change. We'll get new sciences that are finishing research or whatever the case may be to give us new information. We'll have some information gathered after having seen some of these particular products in performance, and we may make some refinement to our guidelines or practices, or we may end up having to revise them in some manner, shape, or form. These are all living documents subject to change as needed, and as we progress forward through time, these changes will be made as needed. One of the ways that we're put forward that are trying to gather information now is what we call our Drainage Infrastructure Information Management System, DIMS for short. It's a data warehouse of information, and we have a mapping interface in which we can actually display our culvert locations on our highways. One of the elements that we've been able to build into this one is that it's a sustainable inventory. It's not a snapshot inventory. Our maintenance information is collected in a required format by our maintenance contractors, and at the end of every year, that information is then put forward as a deliverable to the ministry, and we upload that information into DIMS. This is going to be done on a yearly basis. Design information at the end of each and every contract or assignment. Once they're finished, the design information will be uploaded into our data warehouse as well. So that way we'll also have design information available at any given time. The construction information, what actually is built. From design, we're putting forward that there's potentially pipe material alternatives and other choices put forward. The contractor will only install one type of pipe material and will install it only in one method. That way, we want to know what actually is built, and that will be the construction information, and that's inclusive of post-installation inspection results. And they're uploaded at the end of every contract. So this way, we're able to keep our inventory information and data up to date, and at most, we may be about a year out of sync with what actually is in the field versus what we have in our DIMS system. Be able to move on right down into the actual culvert locations and be able to see, okay, what's in place. Box culvert, arch culvert, circular culvert, the type of material, when it was installed, some of the other parameters around it. And we also have it built so that there will be hyperlinks to the design reports or studies. Any photographs that are taken are also hyperlinked to these particular locations. What that will help us in the long run, we'll be able to do better asset management and planning. It'll give us an information knowledge base about what we actually have out there in the field, because as I said, excuse me, as I said at the beginning, we're estimating approximately around 50,000 culverts plus or minus 4,000 or 5,000, whatever the number is. This way, we'll actually have a better handle on what we actually have out there in the field. Better scoping opportunities. One of the main things we also see from this is that we'll be able to assess our pipe material performance, and ultimately the results will determine whether or not we need to refine the design guidelines, and if required, that would be the actions taken. We've been working a little bit with trying to come up with some design support tools. This is a particular software program. It's based fundamentally on the gravity pipe design guidelines. If I remember back that there's a lot of information that goes into these quantity sheets, and we may have numerous sheets in a contract. Certain contracts I've seen have up to 90 of these quantity sheets in the contract. They're all manually entered by the design team. With this particular high-dis program, the design team will actually be able to input and do the analysis work as assisted by this program, and once complete, we'll be able to export the information into a file that can then readily be turned around and imported by our contract preparation system and populate these quantity sheets. A little bit of a time saver, and we're at the stage right now of updating this particular program to the Gravity Pipe Design Guidelines 2014 status. A little bit giving an idea how our post-installation inspection works. As you can see, once I find my arrows here, there's an individual pipe in this location of the form. There's 31 meters of threshold length, 11 meters of acceptable length for the whole culvert length of 42, or sewer in this case, and that gives a weighted price adjustment factor of 85.24%. Down below here is that we've inspected 2 other pipes. So once we take all those results into play, the actual weighted price for the item is actually 98.05%. It's now up to the contractor to make the choice whether he wants to voluntarily replace this pipe and try and get a better installation to improve his weighted price adjustment factor, or given that it's at 98.05% for 1,240 meters, he may wish to, or it's not worth taking out and replacing. He accepts 98 cents on the dollar for the work that he has done. This is left up to the contractor. The contractor also has the option of requesting a referee inspection, in which case the results of this inspection become null and void. A second inspection firm is brought in, and those results become binding on both parties. If they're the same or worse, the contractor pays for the inspection firm, and if the results are better than what we had initially received from the first inspection firm, MTO would pay for the second inspection, or the referee inspection. A little bit more towards the future of where we're heading with some of the gravity pipe design work. Right now, we're starting to look at the trenchless focus of gravity pipe installations. So we have different opportunities. We've identified about 20 different methods out there in addition to open cut or direct burial. We have spray-on materials, mortar mixing, or polymer mixes. We have also insertion of close fit liners, which could be your fold-in form or cured in place pipe. Can also insert pipe liners with grout placement in the annular void between the host pipe and the insert liner. We have replacement by force methods, which are your pipe bursting, for example, shown in the lower right-hand side. Can do by drilling methods, microtunneling as a new concrete pipe installation as an example. Placement by force methods, pipe ramming, or placement by drilling methods. Placement is different in replacement in that we're now putting pipes where no pipe existed. Replacement is putting new pipe where a pipe existed. Once we have all those different technologies evaluated, we're developing design guides for these at the present time. This particular study started with the first 7 in December of last year. We're starting the second assignment in May of this year, and the third one in November of this year. Will be complete then by November 7, 2017, and the construction material specifications shortly to follow in 2018. Out of the information is gathered from our design guides, they will also be developing the method selection guide. So based on site performance needs, long-term fix, short-term fix, what are the hydraulic needs, ecosystem needs, and parent pipe condition, what's the integrity, what's the alignment, embankment condition, do we have a lot of voids or no voids. The process will help designers go through and select the right, again, based on the science, knowledge, and experience of the day, methods that they can put in a contract for a contractor to install our pipes, gravity pipe systems with. The pictures noted right here are what is a backscatter chromatography technology. It's really basically an X-ray machine set up on the inside wall of a culvert, and it sends an X-ray swath through the pipe wall. The dark areas would denote any void areas, so you can see in the lower screen where the corrugated pipe is shown, a few little voids right in the area of the troughs. And that would give the designers an indication of, do we need to fully replace the pipe, or can we, do we have to fix the voids first and then replace the pipe, or align the pipe, and as I said, this is a whole process that the designers will be able to go through, determine which methods is best suited for the particular construction site. This one is just sort of to summarize that we actually have a blueprint of our Gravity Pipe Infrastructure Initiatives program. We have the preliminary design right up through to maintenance of our pipe sewers and culverts. In this particular zone, the whitish area, we have all our different documents that are being developed or have been developed, and ranging from directives, material specifications, construction specifications, inspection work, research and development, all in this area. Our IT support area down below, and with the IT side, we're also looking at connection of, or transfer of information from these different activities into our DIM system. So really, the upper portion is really the quality building blocks that I've been talking about all the way through the presentation. We have our user documentation support that has been developed over the last 14 years or so, with more to come. And we've also been identifying what type of user assistance support is available from the IT world. From here, we've just provided a few internet connection sites. So if you were to say, okay, click on the drainage management site, this is what you would be seeing, drainage management. You have different tools available in documents. There's the MTO intensity duration frequency curve, the drainage management manual, the design standards that I've talked about, the guideline, these gravity pipe design guidelines, directives, and other documents that may be of some value. This is the IDF curve. It's a online tool. You just go to the location in the province of Ontario where you wish to have some rainfall information. So here I just clicked on the area close to Woodstock and Highway 401, actually on the 403. And from there, when you submit that information, it generates the intensity duration frequency curve for you, as well as the return period coefficients that are used in the two-parameter regression equation to determine flow rates. Again, the Ontario provincial standards, I've talked a little bit about those along the way. You would actually end up into this particular site. On the left-hand side, you see the different Ontario provincial standards. You have access to our CDED manual, which stands for Contract Design, Estimating, and Documentation Manual. You have different special provisions from the ministry or MTODs. So all our construction material specifications are accessible from this particular site. If you actually get a little bit further into it, we have, as I said earlier, we talked about municipal, provincial, and provincial common specifications. There's provincial-oriented specifications, which was our culvert installation by open cut. There's municipal-oriented counterparts to whatever is a provincial-oriented material specification. So you can see that there are construction and materials, there's drawings, etc. as well, all accessible for information. So at this point, I'm going to turn it over to Ray while we get set up to start receiving some of your questions.
Thank you, Art, and thank you to all of our audience. I just wanted to mention to you that we will be posting this presentation to our website within the next week. That can be found at www.cspi.ca. Questions, James Carter from Path Marketing is now going to moderate Q&A this session. We'd love your feedback. And again, thank you to Art for taking the time to speak to all the audience, and again, thank you to the audience. There's Art's email address, and he's more than willing to share anything with each and every one of you. And also mine, remember, if you would like a certificate from the CSPI for the continuing professional development, please send me something along. So I'm going to pass this over to James and give the microphone back to Art, and he will respond to any of the questions that come across. Okay? Thank you.
Is Art back on the line here?
I'm back on the line.
Excellent. I guess the first one I'll cover off, there were some questions about presentations. Yes, we will make sure that they get posted. There'll probably be an email that'll go out from CSPI next week, and we'll make sure they're published on the line. As well, there's a video recording of this webinar, so we'll be able to post that on YouTube and send links along for that as well. With respect to CPD certificates, just so Ray doesn't get flooded with emails, we do have attendance records from everyone who attended here. So it's just anyone else who's in a boardroom today, if you want to take roll and send an email along to Ray basically saying you certify these people attended the full duration, then we'll make sure you get your certificates as well. So again, if you registered under your own name and joined today, then you'll automatically get one. So, first question, were there any non-certified pipes used in MTO projects after 2009, and if so, under what conditions?
I would say after 2009, the only condition that a non-certified pipe in the truest sense of the word got used would be that it slipped through the cracks. With any process or any new process being put in place, there are always a few hiccups in it. So some may have in the early stages slipped through the cracks before the full contract administration sector was fully aware of what was going on. The other ones that I've noticed that might slip through the cracks are those that are not fully marked in accordance with the industry standard, and our contract administrators did not follow through with rejection of that particular pipe product. What I'd like to just again point out is that on the certification requirements of product is that all the markings on the pipe products must be done in accordance with the industry standard, complete with all the interval requirements if necessary. So at some points you may see that a industry standard marking must be every 1.5 meter roughly intervals on the pipe. They should all be there, otherwise RCAs have been instructed to reject these particular products. In addition, the odd time we've been seeing that the logos are not on the pipe products that are being delivered to the site, and they must be on the pipe products. The logo must be on each and every pipe product. So that's something that is the only way right now that the non-certified products are slipping through the cracks.
Great, thank you. On the MTO quantity sheets, we see a pipe spec calling out 1,000 millimeters and then it has bracket plus 200, which is tolerance, I guess. Or does that mean we're allowed to look at applicable pipes in the entire range from 1,000 to 1,200?
What the design team has done is looked at the hydraulic aspects of the pipes, and they're the one size from 1,000 right up to the 1,200 size of pipes. So what they should have, by specifying this, we're going to make the case that the design team went through and did the hydraulic analysis on the 1,000, the 1050, the 1080, the 1120s, or the 1,200, whatever sizes are in that range that has been specified by the design team through those numbers. So that way the contractor, if he has, say, some 1050 pipe available from another job that's in his storage yard at his office and wants to use that on the site, it's okay, because as long as it meets the other specification of material side, then those pipe products would also be acceptable on that particular job.
Great, thank you. Why is the Welding Bureau allowed to certify steel pipe?
The Welding Bureau is sort of just the organizational name on it. They've also gone through different aspects with the Standards Council of Canada to show that they have the expertise and resources necessary and available to be able to certify different products. Pipes are not the only things that this particular organization certifies, and as such, like I said, they've been accredited.
Excellent. Here's a good question. There was an EMSL for steel pipe referenced on table C13. This is around 10:10 a.m., so towards the beginning there. That was based on a Florida DOT spec. There was some question about whether Florida obviously wouldn't use road salt. Is it still applicable?
In that particular one, it's probably that be aware that in 2014 we've had some updates on the estimated material service life designations for steel pipe products, and you would see that on the new graphs that were introduced in the 2014 document. We did note that there were a few areas in the Florida calculations that are not quite what we think it should be, and this is where one thing that I should point out is historical performance is also a strong knowledge base that the design team should be aware of, to say, okay, the gravity pipe design guidelines after assessment are giving me the same pipe that now it's supposed to last 75 years. The same pipe was in the ground already and only lasted 25 years. That historical knowledge is something the design team should take into account and adjust the different parameters in order to, right now, this new pipe that was 75 is now showing up as 25, which is the realistic way because of historical performance.
A good question. Why is clay seal not allowed on HDPE pipe?
The clay seal, from what we've been told by the different industry representatives when we went through this particular process, had some interaction with the HDPE products, and thereby they were not as suitable for doing the drawing a blank here for a second, mitigating or preventing the piping flow around the culvert, and so they also have the anti-seep collars that can be used in place of that.
Does the pH and resistivity need to be measured during the maintenance schedule?
We put that forward as a something that we would like the maintenance staff to start doing, that every time they go out and do their detailed inspection on a culvert site, they would actually do a pH and resistivity measurements at these particular sites. We're a little bit on the, they haven't actually put it in as a recommended or required deliverable from the contracts. We're trying to push forward to get it as a required deliverable. So what you would see from our side anyways, as the collection would go through, that new culverts would get that pH resistivity measurement done for year 1 and then not again until year 11 every 10 years until such time as the CMI drops to make it 5 years and so on. So the pH resistivity is something that we have put forward. We're in discussions with our maintenance head office staff to try and put it in as a requirement on contracts.
So I'm going to take about 2 more questions here, just because we promised everyone a 10:30 wrap-up, and we're getting on here. There are some really good questions here. So what we'll do is we'll probably take them over email and make sure that we reply all so people can see them, and we'll respond via email for the balance of them. With climate change, would you consider PMF, that's probable maximum flood, instead of 100-year frequency?
Currently with climate change, there's active work has been done by, the Ministry of Environment and Climate Change Group, and there's a number of different forums that have been working in this area. We at MTO have already started doing some assessment work in that particular area, zone of influence as well. One of the things that we've done and did some resiliency tests or studies and analysis on some of our existing storm sewers and culverts and bridges. And because we use minimum sizes, a lot of times when we start our storm sewer work, the 100 millimeter diameter size would be adequate to convey the flows for the first part. However, our minimum size for storm sewers to start with is 300 millimeters. So we already have a built-in added capacity element to our storm sewers. Thereby, the resiliency we've been finding with climate change tends to give us, well, we have a lot more than we thought. In some cases, depending on the type of increases, we may not actually have quite enough. My counterpart in the office is actually more involved with this. The IDF tool that's online, it's in a phase 3 development at this point in time, and part of that phase 3 development is building in a future prediction of rainfall intensities based on a historical trend of data. And so that piece is being worked on right now, and what we're seeing based on the statics of the historical trends, we're seeing that potentially we could have up to 10% increase in rainfall intensities in some parts of the province, 25–30% in others, and we do differ a little bit from the MOECC information of the IDF results that they've put out. However, we're working with them and moving forward in that direction.
One last question. A few people asked whether DIMS was available to consultants.
At the current time, we're in the final stages of having it operational. It will be made available to design consultants that are going to be working on MTO projects at the time when they begin their work. That will probably happen in, I was told it would be later this year. However, with the IT world, there's always something happens, so it might be slightly later than that, but the information contained in DIMS would be made available to our design consultants. For other users, there would be a limited level of data that would be made available to them, so there is possibilities that there would be, in the long term, access from other outsiders to take a look at what's on highways, for example. At this stage, my hands are tied. The IT world and the government has said so much is available, and we're going to keep it to ourselves. This much available, we'll have to talk about whether we open the doors or not.
Excellent. All right, thank you so much. Obviously, we had huge interest in this topic, and you guys have put a lot of work into preparing this presentation for the group. So for those who joined today, if there are additional questions, like I said, we'll get to them. Feel free to email Ray and or Art directly with additional questions, and we're going to end the session now. Keep an eye out. There's a quick survey at the end, so we'd love your feedback on that as well. Thanks, Art.
Thank you, and thanks everyone for listening in on my talk. Thank you.